Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series, which is now just called the Qiskit Quantum Seminar to keep things simple. And this series is dedicated to you, the research and academic quantum communities. Now, in just a minute, I'll be thrilled to roll out this week's seminar with our very own Dr. Oles Stanko from IBM Quantum, who will speak about a work I am particularly proud of. Before we get there, I'm so glad you joined us on time. And let's start with our favorite question, which is where are you guys tuning in from today? You can reply to that in the comment chat box here on YouTube, above, below, left or right. That's the same place where you can ask questions live of Oles and myself during the talk, and we can keep this very interactive and have some fun with it. That's why we have this background music on today. If you haven't seen the panel with Jay Gambetta and our internal and external researchers on doing experiments at the 100 qubit plus level, that's a great prequel to today's presentation by Oles. In fact, one of the largest experiments, actually the largest to my knowledge, two experiments on superconducting devices today are the utility paper, which you've heard a lot about, and this project, which we mentioned in that panel. And today we'll have a deep dive into with Oles, myself, and you. So folks, don't forget to click like and subscribe to know what's coming up. But the only time to be live is right now at noon Eastern time every Friday. Today, I think it's time we get started. It's my pleasure to roll out episode 145. I am your host, Zlatko Minev from IBM Quantum, and I have the pleasure to introduce you to Dr. Oles Stanko from IBM Quantum, who will tell you about a work I'm very excited about. Hello, Oles. How are you?
Hi, everyone. Thank you very much for inviting me here.
And just like everyone else, please do tell us where you are tuning in from today.
Oh, we have a lovely morning in San Francisco downtown, as you may see on my background.
Excellent. So Oles, before we pull up your slides, allow me to introduce you to the rest of the group. Oles Stanko received his PhD in physics from MIT in 2019. Oles then completed a postdoctoral fellowship at the University of Maryland as part of the JQI, Joint Quantum Institute, and QUICS, the Joint Center for Quantum Information and Computer Science. Oles joined IBM in 2021 as a theoretical physicist and a quantum computing researcher, and is my dear friend and colleague. So Oles, take it away.
Thank you very much for this nice introduction. As Zlatko mentioned, this work, which I'm going to present today, is IBM's work, where we work on uncovering local integrability on IBM quantum hardware. Also in the slide, you see the name of my co-authors, including Zlatko, who work day and night to make these things happen. And I would like to thank everybody for joining us today and listening to this talk. So first of all, let me give a very broad introduction in the field we're working with. And I think some of my listeners today already have experience or expertise in many-body quantum systems. But to be consistent, let me just give a brief overview of what we're doing. So quantum many-body systems is a field of physics which studies interaction of many particles, such as atoms, molecules, electrons, etc. And therefore, we study nature around us, because everything is composed of these particles. And following the old Richard Feynman's idea, we can translate the motion of these particles onto the dynamics of qubits, right? And engineering the dynamics of qubits, we can realize simulation for different systems around us, which can be very beneficial for different areas of science, such as material science, nanotechnology. We can use it for simulate chemical reactions, use it for sensing and metrology, and also do some fundamental discovery in high energy physics and cosmology, for example. And this study is also about simulation of a system. My graduate advisor, Seth Lloyd, has a book saying that essentially, you can think about universe as a quantum computer that simulates itself. And this means if you have a large enough quantum computer, you can simulate universe. Of course, at IBM, we don't have such large quantum computer, but we have access now to hundreds of qubits, and soon will be thousands of qubits. And we can arrange these qubits, and see how they evolve and learn their dynamics, thus making progress towards these interesting fields. But what really learning quantum dynamics means? And this is, I think, interesting question. So if you open a textbook, you will see that describing a quantum system usually starts with finding eigenstates and eigenvalues of the Hamiltonian that describes your system. And this looks nice if, for example, you're able to solve this problem exactly. But if you deal with many-body system, you have experience with it, you already know that this approach is not very scalable, in a sense that it will require exponential amount of memory to just store all the information about eigenstates and eigenvalues. Just give you some perspective, if you have if you have hundreds of qubits, you will require around 10 to the 47 terabytes of data to just put all this information together, which is insane, and we're never able to do it. And even if you have just access to quantum hardware, you will need, and you can access the data points one by one, you still will require around 10 to the 13 years to just resolve two close energy levels. Therefore, we should ask for other ways to describe quantum systems, and traditionally we do that. We, for example, look at the ground states of the Hamiltonians, which usually describe with tensor networks, and use description in this way, or we use some mean field approximation where it describes system in terms of quasi-particles, and do some other interesting models. However, today I would like to represent the model and a system for which you can describe it relatively efficiently using integrals of motion. So the class of system we study will be called integrable or quasi-integrable systems. And let me dive in and tell you what are integrals of motion and why are they interesting to study. So integrals of motion, the notion of integrals of motion comes from classical mechanics. For example, assume you want to solve a problem in classical mechanics, such as Newton's cradle. And to do so, you will probably need some sort of equation motion. For example, you can use Newton's laws, or, as you see on the screen, Lagrangian equation. However, even before you do this, the right thing to do is to determine what properties of the system remains constant in time, or finding conserved quantities. These conserved quantities include, but not limited to, say, energy, momentum, angular momentum, charge, mass conservation, etc. This quantity is usually called integrals of motion. Why it's useful to find integrals of motion? Integrals of motion, every time you define a single integral of motion, you reduce the number of equations you need to solve by one. And this essentially means if you have a classical system that has number of integrals of motion equals the number of degrees of freedom, or number of equations you need to solve, your problem is done. You can find a lot of things without writing equations. And therefore, integrals of motion are very valuable. And in classical mechanics, there are a number of ways that you can use to find them, from analytical to numerical. Now, if you go to quantum mechanics, notion of integrability is slightly different. So when we talk about integrable dynamics and quantum mechanics, people usually talk about something which is solvable analytically. Sometimes they say it's also solvable in Young-Baxter equation. More broadly, researchers define integrability as absence of quantum information scrambling, chaoticity. Physicists like me sometimes think about integrability as a certain statistic of energies. But broadly, you can define integrability in quantum systems in the same way as you do in classical mechanics. In particular, you can define what we call integrals of motion, which in quantum mechanics not quantities, not numbers, but operators, which do commute with Hamiltonian of your system, or if your system is more general, like a circuit, it commutes with a unitary of your system. What this means that essentially the expectation value of the operator remains constant, and you can use them to solve problems. And a quantum system is called integrable is when it has extensive set of local integrals of motion. And you see here two asterisks that I have put here, and let me explain this as well. So what means you need extensive number of integrals of motion? This means that it should scale somehow with number of qubits you have in a system. You cannot say that the number of integrals of motion should be equal to the number of equations you have, because number of equations in quantum mechanics is exponential. It's unreasonable. But you may say that I ask number of integrals of motion in my system to scale linearly with size of the system. Also, we have to say something about the structure. So, for example, if we take a quantum state, eigenstate of your Hamiltonian, you always can combine such an operator you see here, and this operator will commute with your Hamiltonian or with your unitary. And this will not depend on any property of the system, just basic rule of quantum mechanics. And we should prohibit this. We should make sure that we don't have ability to do this. So what we defined instead, we defined local integrals of motion, which have a structure as a sum of certain local operators which we can measure. For example, it can be Pauli operators in certain region of space. And the main goal of today's project is to go and try to detect from a system its integrals of motion, knowing that have this form. So it's very, very general overview. Zlatko, I'm curious if we have some questions at this moment.
So far, so good, Olis. Folks, this is a great time to post any questions that you may have. Please don't hesitate as we go through, and we'll always bring them up to you, Olis, and also at the end.
Yeah. So I just want to show that once we have, once we have this integrals of motion, we have a pretty extensive description of the system. That's why we're interested in. So, so to do so, we need to find a good system that has integrals of motion. And we don't want to pick up something exactly solvable because, well, we want to show the utility of quantum computer. Therefore, we chose a system which is also called quasi-integrable that exhibits many-body localization. I don't think maybe not many readers here know what this many-body localization is. So let me try to introduce it very broadly using this Hamiltonian. And if you have more interest in this field, I recommend you to listen to other Qiskit, another Qiskit seminar, which happened months ago, led by David Hughes, who is one of founders, along with Igor Lehner and others of this field, and you can hear more. So what is many-body localization? Consider the Hamiltonian you see here. And this Hamiltonian describes a qubits or spins that are sitting in one dimension, form a one-dimensional line. It, as you see, it contains three terms, where first term describes interaction between qubits. The second term is a kind of interaction of each qubit with local field. And very importantly here, this field is disordered. It changes from qubit to qubit, taking random values. So final term is also a field, but it directs in transversal direction. And its role is to introduce some quantum fluctuations to the system, because without this term, your system is what we call classical. It means that it doesn't have any quantum superpositions. So why this Hamiltonian is so interesting and so takes so much attention in the past decade? Well, if you ignore this transversal field, you just forget about it, and you think about just this first two terms, you quickly realize that if you have individual Pauli Z operators, which describe individual magnetization of your spins or polarization of qubits, it commutes with the Hamiltonian. So, and because it commutes with Hamiltonian, if you remember the definition we just made a few slides ago, they are integrals of motion, and they also local because they act just on a single qubit. So in a sense, this system is, by definition, we provide is integrable, right? So far it's so easy, right? So now we ask a question: what happens if we add this field? And here's the most interesting thing happens. So the current consensus in the community that it will depend on how large the field G is. So if the field G is very strong, your system starts being chaotic. Your disorder essentially makes system evolve very randomly and similar to, random circuit. However, if G is not very large and smaller than critical value, situation changes, and your operators, they do not disappear, but they kind of transform into a new set of local integrals of motion, which have a little bit more complicated structure, but they do exist. And you can describe the structure using this exponential shape on the right. And what this exponential shape means is that your own integrals of motion, they're sum of Pauli operators, and the largest weights on the Pauli operators in the center is this shape. And then as you go far and far from the center, your weights go down and down and down. So this means that essentially this operator is mostly sitting in a few qubits. And you have many of them. As well, you have many Z, you have many of these operators. So discovering these operators, you can't describe your quantum system completely. I mean, at least a level of eigenstates. And our goal will be to recreate this many-body localized system and try to explore what these LKs are in the system. I will pause at this moment again and wonder, Zlatka, do we have any more questions?
Yes. So one question from Bektor Murzaliev is, can energy be a local integral of motion?
You may consider, so it's, yes, so you may consider the integral of motion. The thing is, it's always a single integral of motion for many systems. And to claim that system is integrable, we need, as I said, extensive numbers. So just finding energy or some similar operators, we cannot claim the system integrable. But yes, you can think as energy as a single integral of motion, universal single integral of motion that is present for all Hamiltonian systems.
Right. But is it a Liohm, a local integral?
Yeah, it's yes, you may. Okay, so here we call Liohm integral of motion if it's supported on a set of qubits, and maybe I need to clarify this more, if it's supported on a group of qubits which are spatially together. So if you look at Hamiltonian, it's a sum of terms across the system. So they do not meet the notion of locality that we use here in our talk, but in some sort, if you think about more general notion of locality, you can also claim it's local, just not in the terms of this talk. So
and maybe final question from Jeffrey Berger here. Do the AMU coefficients have to be real?
Oh, yes.
Hermiticity.
Thanks. It's a very nice question. So we assume that LK are Hermitian operators, so like operators Z. So AMU must be real. So if we take a Hermitian conjugate, you get operator back, because Pauli are self-adjoint operators.
I guess one is folks are very active today. I love it. Thank you, guys. Maybe one more final question here from Bektor. How do you define GC, the critical value there?
Oh, it's a very good question. And just in next slides, I will show you example how we try to. I mean, maybe I don't know. Maybe I don't understand question. So I understand question as how we find it if we have a system, and I will explain it in the next slides. So, but maybe if a question more mathematical, how you define mathematical, maybe it's a very complicated question, but it's something which separates two distinct regimes in your system, and you can see it either from numerics or from experiment.
Thank you.
Okay, great. Thank you very much for those great questions. Let me move more specifically to what we do with our device. So our goal is to simulate something similar to this Hamiltonian I presented you. And we, of course, at this stage of technology, we can simulate this Hamiltonian by dividing unitary evolution using factorization, which mapping it to the individual circuits. However, this will be a little bit expensive in terms of number of gates. So we come up with a bit different scheme. So instead of this Hamiltonian, we start the circuit you see on the screen. And this circuit qualitatively has a similar structure to this Hamiltonian. So first of all, let me say that as usual, we read circuit from the left to the right. So we have input state on the left, which we get applied, for which we get apply a number of identical blocks, each block containing the same gates. We sometimes call this evolution Floquet evolution. That's why we call this Floquet many-body localization. And in each block, we have 2-qubit gates, and 2-qubit gates here serves the role as your ZZ term plays, in a sense. Then you see the series of these different shaded gates that are random phase rotations. And here we just assume that the phases are just sampled randomly between -pi and pi. And these gates, they play a role of disorder. And importantly, the disorder doesn't change for the same qubit, but for different qubits, it's a different value. So finally, you have the theta gate, which have a rotation, and this theta gate is essentially plays the role of our X field. It's not exactly X field, but the idea is that if you change the angle theta, you get a transition between localized and delocalized regime. And why are we interested in this particular circuit instead of Hamiltonian? Well, because it's much easier to implement with our hardware, right? We know that IBM has native gates as Control X gates, and you can easily convert Control X gate and Control Z gate. So you can just run more gates on your device, which means deeper circuit, and that's very beneficial. So now let's try to dive in and try to ask question what we can do with the circuit. So first claim is that similar to this Hamiltonian, the circuit has a phase transition point. I mean, at least what we see from numerics and experiment. And it lies around 0.16 pi if you change the parameter theta. And I will present you now few tests which we've done, which give us power to claim this. 2 of them will be non-scalable, which we did in numerics. And 3 of them are experimental, including finding integrals of motion, which we implement on hardware. So let's start with the unscalable ones. So first non-scalable feature is level statistics, something which I mentioned, if you remember, when I introduced integrability. So what is that? What is it? If you take your unitary operator, which describes your single cycle, you can find it eigenstates and eigenvalues. And if you look at eigenvalues, they are phases. They basically the phase rotation, and phases are somehow distributed over the unit circle, right? So then you can look at what we call adjacent gap ratio, which is minimum between 2 adjacent gaps between these phases divided by maximum of 2 adjacent gaps, and look how it's distributed. So if the system is chaotic and what's called ergodic, which doesn't have any conservations, then we expect this distribution looks like this. It's also called Wigner-Dyson statistics. And as you see, if we set theta to be, say, 0.3 pi, our result exactly matches the statistics. So we know that for 0.3 pi, the system is, in fact, chaotic. Now, if we now set our angle smaller to 0.51 pi, we'll see that the distribution of these quantities will be different. It matches this blue curve, and this blue curve also called Poissonian statistics, and it's exactly what you expect from MBL systems, many-body localized systems. And then you can just change the system size, and you see how these curves transform, and you see that there is a point of transition where there's a crossing between this curve happen as you increase system size. And this crossing, this means if it's around 0.16 pi, it exactly shows that where transition happens. Quick note that, of course, it's only for small system sizes, and with increased system size, it might drift, but it still give a good hint. Okay, but it's of course non-scalable measure because, well, you need to find these eigenvalues, and how are you going to do it for a large system? Another non-scalable is not look to eigenstates and just look at eigenvalues and see how entangled the not eigenvalues, look at eigenstates and see how the eigenstates are entangled. So in particular, if you take an eigenstate and look at the entanglement entropy between two halves, you can also see that there is two distinct regimes as a function of angle. For small angles, your entanglement entropy per qubit is actually decreasing. It's not very visible here, but it's going down. While if you have a larger theta, parameter theta, it goes up, and it's eventually saturated value, which is called a page limit, which is the maximum entanglement entropy that the system can have. And this also gives us assumption that where the crossing is, it's not very visible here. Here lies the phase transition. You also can look at how the entanglement entropy varies from eigenstate to eigenstate. And that will give another peak, which will also hint the presence of phase transition somewhere here. The only thing that this peak, as you see, it drifts a lot, so we expect that it goes to this dotted line. It's a very large system sizes. Anyway, so this is two non-scalable measures. They require now in eigenstate and eigenvalues, so therefore we cannot really do it in hardware, but we have at least hint that we have a transition in our system. So now let's go to scalable parameters. So what are scalable measures of MBL? First of all, we can look at dynamics of local observables. We can look at dynamics of local spins and see how well they remember the initial state. So for example, we can arrange system in some ordered state where colors correspond to state of qubit and see if this order survives. And if it survives, it's a good indication of MBL. Not a proof, but it's a good indication.
Before I'll let you get too far, maybe a couple of questions that piled up on the previous question. If we go back to signature 1 on the level statistics.
Okay.
Can you clarify again for us what delta lambda A means? Since it's in the complex circle.
Wait, sorry. Maybe I'm not clear. So it's in complex circle, but phi alpha is a phase, and phase is a real number which takes values from 0 to 2 pi, and essentially you can put it on a circle. That's what I meant. Mm-hmm. Is that?
Yeah. Yes. And I guess the measure delta lambda A, is it are you taking? Is it an angle difference that you
right? Yes, actually it should be delta phi alpha, and I somehow just slipped my my attention. Yes, so this should be essentially the difference between two closest values of phi.
Great. And what do you do at that one singularity where the phase wraps, or is that not too much of an issue because you maybe unroll it? Just because the phase goes from 2 pi to 0, and there's one piece which is singular. Or maybe let's come back to that. Maybe that's too technical.
No, I think it's too technical, but no, you put eigenstates just on this. Yes, so I don't think there should be any problem with this. But maybe if you want, we can discuss it after once we finish talking. Maybe there is some interesting technical question to ask here.
Okay, great. And Vector, you had a couple questions, but I think maybe we touched on them. Did you want to say anything else about entanglement spectrum, Olis? There was a question around that.
You can define a little bit also other signatures related to entanglement. I just didn't want to stop on that too long because it's something non-scalable, something which we cannot do with hardware. So I think I want to just briefly mention the entanglement itself. And of course, if you look at literature, researchers studied many-body localization from different perspectives and invented other interesting measures of phase transition there.
Thank you.
Okay, so let's go back to local signatures. So second signature, or scalable signatures, and second signature is one particle density matrix. And it's essentially correlation between spins. And I will just stop on this in a brief moment and explain why it's important. And final measure is what's the main goal of our project is defining local integrals of motion. And as you go from local spin measurements to local integrals of motion, you increase the complexity of your experiment, you increase the hardness of obtaining these results, but you also increase, in a sense, what you gain about the system and confidence the system is an MBL regime. So let me start from dynamics of local spins. So here is a depiction of the initial state of this qubit chain, which we have, which we evolve according to the circuit you've seen before. And again, if we choose our small angle, 0.5 pi, we'll see that the pattern we put system in, it survives over time. So, I mean, it decays slowly, partially because of noise, partially because there is internal dynamics. But the idea is that if you take long times, probably which we don't have access here, it should plateau in the ideal scenario. And this means that your memory, without an absence of noise, should persist forever. While for 0.3 pi, your order should disappear almost immediately. And take a note that it's logarithmic scale, so it's very, very fast decay. And you can also, and what you see on the right, what you can define as a charge imbalance is just difference between expectation values on odd and even qubits, and it's a good single number that quantifies how your evolution happens, how ordered it remains over time. So, and again, see we see very, very hard distinction, and what's important, this preserving order actually give us hints that we have hidden integrals of motion in the system. Why? Because as you see in the next slides, your integrals of motion, they are actual sum of Pauli's, but the largest contribution go from Pauli's Z operator. And the conservation of LK is essentially very rough conservation of Pauli's Z operators. Therefore, conservation of Z order is a very good hint that you have conservation of LK. Okay? Some kind of cheap version of experiment we're doing next. So let me also briefly touch another measure, which I think is very interesting because there is not much attention to it in literature. It's called one particle density matrix. And to understand that physics, you probably should keep in mind that qubits, which we operate, are essentially bosons. They are like bosonic particles and oscillators, for which we prohibit higher occupations, for which we prohibit bosons sitting on top of each other. And for these bosons, you can introduce what we call fork operators, creation operators, and define this object, which we call one particle density matrix. And what this object means is essentially describes that a single boson flowing in the bath of other bosons, how its density matrix looks like. And again, if a system is localized, this boson should relax into state which is more or less described by thermal distribution, while MBL systems, it should somehow remember about what happened before. And that's exactly the test we did. So we look at this density matrix, we look at its occupation of different eigenstates of this density matrix. And when we initialize system in the state which we've seen before, you can see that the distribution of eigenstates should have this rough form. It's just a threshold. And if you let system evolve, what we expect in thermalized system that it relaxes into this universal thermal shape. And again, this is a good signature that your system is MBL regime. And this happens in angle which is 0.25 pi. So these numbers are your theta in terms of pi. However, if you take a small angle, you will see that your system, your boson, which flowing again is a bus of other bosons, it feels like it cannot relax on some thermal state. It remains, has a memory about initial state. And that's what this plot shows you. And why are we interested in this plot? I mean, interestingly, if you plot the derivative of this curve at this point, taken as a discrete derivative, and look at its slope, you will see that the slope of this derivative, it has a crossing very similar to level statistics or entanglement entropy. And this crossing is very important because it also allows us to identify the position of phase transition, which is, you see, is around 0.16 pi. So we get this exciting correspondence between something we can measure and we can actually, and we do simulations. And this give a good sign that what we do in the lab is actually we want to do. But the system we study is actually the system we have in mind theoretically. Zlatko, do we have questions?
Folks, it's a great time to add any questions, but I think right now, Alice, we're good to go.
We got to go. So now let's hold on. We go to local integrals of motion, which is the main goal and most exciting part of this talk. Okay, so now let me take it slowly and show how we extract integrals of motion. So as a result of the experiments we've done before, we remember we already have some dependence, some signal from device. In particular, we have expectation value of z operators, which looks something like this. And here's this just toy model having 8 qubits. So we can now, to this signal we've already measured, we can add some more signal. We can add measurements of 2 qubits and 3 qubits, which give us already more complicated picture right here. And we can keep going on and on and on and add in more and more and more measurements, single, 2, 3 qubit measurements from all across the system. As a result, we have this very tangled picture, which is like just essentially a huge database of measurements you got from your device. And now your task is you know what it reminds me, Zlatko, there is a movie called A Beautiful Mind, and the main character is played by Russell Crowe. Actually, it's John Nash, who is also real person who won Nobel Prize. Due to this movie, he arrives in Pentagon and get presented with a huge wall with many numbers. And he looks at these numbers, and suddenly he realizes the patterns of these numbers in his mind, which is because he's a genius mathematician. And these patterns form some strings of numbers, which apparently become a codes which Soviet spies used and the Pentagon wanted him to find. And if you're familiar with the scheme, with the scene, is exactly what we're trying to solve here, right? We see all this entangled tangled dynamics, and what we want to do, we want to define few operators. Here it's only 4, but in real life it's much more than 4, such that we can find coefficients. We call it A1, A2, A3, A4, such that expectation values, what we see on the left, as expectation values, if we sum them together, give you a constant, something constant in time. And every time you do it, the operator which you get is your local integral of motion. Congratulations. And you can repeat it more and more times and find more and more of these integrals of motion. And this task looks a little bit overwhelming, right? How do you find these operators? How you choose a set of operators you need? And you can still come up with some interesting tactic how you can do it. But here's the method which we use. And we find it very interesting, appealing. And we actually borrowed it from literature. And this is very big, but I think it's the most interesting part of the work. So please tune in. And if you don't, just make sure that we have a method to do it. So what we do, we first start with a suitable operator, some as an initial guess. So we have a guess, for example, operator Z is a pretty good integral of motion. It's not perfect, it has a lot of error, but we assume that is our initial guess from which we start, right? And then what we do, we take operator L, which we want to be integral of motion, and take it as the sum of our initial guess, plus its time evolution in Heisenberg picture with 1 step, time step, 2 time steps, etc., etc., etc. And just simple mathematical fact that if you keep going, if you keep summing all these terms, if you push it to infinity, L will be in exact integral of motion. Of course, in real life, we need to truncate it somewhere, but it's a good strategy. And then, knowing this strategy, you can express this coefficient A mu, which we were talking about in the previous slide, as nothing but a what we call two-time correlation function between your initial guess and the Pauli operator for which you want to compute your coefficient. A little bit complicated, but it's what it is. So then, of course, you need to estimate this trace, which is, again, not easy task. And in literature, you can find different methods how to do it. We do it in a little bit simple way, less sophisticated way, but it's still efficient. So what we do, we decompose our operator L0 using its eigenstates and eigenvalues and just sample from them. So we represent the full sum by some representative number of states. And now we can sample the states using quantum computer. We can start the system with state psi chi, psi k, evolve it with these cycles, measure Pauli p mu, and then sum of them to express the coefficients. That's the technical trick. Again, I hope you tune in. If not, I mean, just believe we have a good method to find it using these schemes running, starting with different initial states, running circuits d times, and measuring Pauli operators. And that sounds maybe pretty good. However, if you try to do it naively in practice, it's a little bit hard task. So if you want to achieve coefficients A mu with precision, say 1%, you can do it a very simple way. You can sample random initial states instead of psi k, and you can measure random bit strings to determine your Pauli operators, essentially deriving what's called classical shadow of your state. But if you compute how many circuits you need to do it for 100 of qubits, you arrive something around 1.6 million of circuits for 100 of qubits, which is a lot. And another contribution for our work is that we reduce this number by taking account that operators which we measure at the end, they are local. They not spread across the system. So this is one benefit. And second, we know the dynamics is slow, so it doesn't take operators spread too much. So instead of sampling the random bit strings and measuring random Pauli operators at the end, we input correlated strings, which correlation length, say 4, is here shown here, and measure low correlated Pauli operators at the end. And that allows us to reduce the number of circuits up to 576. It allows obtaining 1, 2 qubit Pauli operators, as well as many of 3 and 4 Pauli operators, and do not compromise on the error. And that's all trick which makes this experiment possible. And I wanted to mention it because it's very important. And you can find more details in the paper. So now I think it's all done with the technical part of this talk. Let's go to results and see what they look like. So okay, so here's the result for 104 qubit chain. So what we do, we essentially start with initial guess to be Pauli Z operator of, say, qubit 50, and look like how local integral of motion looks like if you use a technique. And that's exactly its representation. It has exponential shape and space, where what we depicted is essentially kind of function which shows us how strongly it acts on different qubits. And it's localized definitely in space, but you can also show that it's localized in what we call the Hilbert space. For example, you can look at contribution to this local integral of motion from 1, 2, 3, and 4 qubit Paulis. And you see it's also get exponentially small as you take more and more non-local Pauli operators. Okay, so that's single integral of motion. Hooray. So now we can repeat it for more and more operators. We can do it for initial guess sitting in qubit, say, 2, 25, 50, 75, 100. And you also see very similar picture, though. It's a little bit slightly different because disorder. And at the end of the day, you can recover all of them. And here now I use x-axis as just to put all of them together without overlapping. So here's all 104 integrals of motion for 104 qubit chain. And for me, it's look amazing because it's essentially sort of a cheap version of tomography of the system that you can do. So now, because there are many of them, we can look at how average integral of motion look like. That's what your picture on the left shows. And the yellow shows your just local integral of motion, while different colors here show contribution from different localities. Same thing which you've seen before, just now averaged over many integrals of motion. And what's funny, you also can look at anatomy of this integral of motion. Look what Pauli operators it is composed of. And the composition of the Pauli operators is very sensitive to the model you use. So you can look at different models. For example, you can run a little bit different circuit. It will have a little bit different composition. And you may think it's a fingerprint of your system. It's another interesting property of the system you can do. And this is very exciting. Finally, you can compare what you do experimentally and what you do in what numerical simulation gives you to just make sure that you do everything right. So now, keep in mind this is a one-dimensional system, and it's evolved very slowly. Entanglement is built very slowly, so you can, in general, simulate it classically. So there is no quantum advantage in one-dimensional spin chain here. So you can accurately simulate it using classical methods. And what you see here, lines are essentially classical simulations, while dots are experimental data. And as you can conclude from this plot, well, we did pretty well, right? We get most of the points right, except of this tails. And this tails, again, this is logarithmic scale, so not as horrible, but I think they are caused by the noise, which make your real integrals, your real operators you measure is a little bit wider because they cause decoherence in your system. I would like to pause at this moment. Now I will give you a little bit more analysis of integrals of motion, but I think it's a good point for questions. Zlatka, do you have any?
Yeah, there's a few, and folks, feel free to bring these up as we go through here. Maybe just tell us a little bit about the relationship between this and the ETH, and to begin with, or sorry, the ergodic hypothesis from Vector.
Yeah, it's a good question. So sorry, yeah.
Yeah, and Vector, feel free to elaborate what exactly you mean here. But the question was along the lines of, can we apply the ergodic hypothesis?
Yeah. So we have, as introduced, we have two phases: many-body localized phase and ergodic phase. And ergodic phase is where the ETH, what's a eigenstate thermalization hypothesis, applies. And on this side, we don't study because, well, all local observables, they tend to go to zero almost immediately at this point, as we've seen from imbalance. Remember, we got this quick dissipation. And this phase is a little bit hard to study in the way. So we study MBL phase. And in MBL phase, eigenstate thermalization hypothesis breaks down. This means that now we have much more interesting non-universal physics happening there. Do you think it's a good question? Answer, or maybe I should add something?
Yes. Actually, I think he just said yes. That's good. So thank you, Alice.
Okay, great. Do you have any questions about the local integrals of motion, or maybe there will be later ones?
Yeah, maybe we save those for the end. And folks, if I miss your question, bring it back up.
Okay, so now I stop at this moment for a quick assessment, and I think everybody should make some stuff for quick assessment, and especially many-body physicists. So we found the set of approximate liams, and the result look good compared to numerical simulation. So, but we haven't yet get an answer how good these local integrals of motion are as it, without comparison to any numerical simulation. Just do we find like real conserved operators? So this one important question. And second one, if there are errors, and there will be errors, of course, what's the main contribution to this error? So the simplest test you can do is to try to do this trick which we did when I introduced integral of motion. You can put all your Pauli operators in comparison and plot the expectation value of your integral of motion. And that's what you get as a result. So this is some typical integral of motion which we pick up randomly from this big set. And you see it's not exactly conserved, so it fluctuates. But it fluctuates its fluctuation much smaller than the fluctuation of Pauli operators. So we get some impressive job, but we still have some error. And now our task to understand where this error comes from. And now we can do some theoretical job and try to figure out what this error is. So as a measure error, we use this quantity, which is essentially normalized Frobenius norm of a commutator between the Floquet unitary, which generates your evolution, and your integral of motion. And the reason why we choose it, because it's easy, relatively easy to compute classically. So that's why its measure is fantastic. But also you can have a lot of tools to compute it analytically. And when you do analytical calculation, you find that you have two sources of error which contribute to these fluctuations. The first source of error is essentially the fact that we truncate your series somewhere. You don't go to infinity. And this method error is proportional to the precision of initial guess, epsilon 0. And that's why you need to set your initial guess as good as possible, divided by the depth of the circuit. So as you go deeper and deeper, this error becomes smaller and smaller. However, as you go deeper, you get a problem with noise. Your noise starts infecting your system really hard. And you can show that the noise error is proportional to noise rate times square of depth. So if you took these errors together, you can easily find that there is a maximum depth, optimal depth, for which you minimize the sum. And this depth is around 10 Floquet cycles, and is more or less precisely what we do in experiment. So we cannot go deeper. And you have to deal then with both types of errors. So now let's try to see which one is which in our experiment. So to do so, we put all Liams on this diagram. So each dot here is individual Liam, which we found previously. And we put it in this diagram where y-axis is essentially what we expect from noiseless device for our experiment. And essentially it's a method error. It doesn't have a noise error. What's on the y-axis here is what you get from device. And it's method error plus noise error. And if your device is noiseless, you should expect everything just aligned perfectly along here. But of course, your real experiment has noise, so your integrals of motion shifted to the right. And you see some of them even shifted to this red area. And this red area is exactly where the obtained integrals of motion has error, which is larger than the error of initial guess, which is bad, right? But luckily for us, it's not so many of them. So we are pretty good. And our error is, you see, it's not too large, and our device works properly, which is amazing thing. Now you can try to work with these outliers a little bit more. You can try to ask question, what happens here? What happens wrong here? And then you may say, well, maybe this integrals of motion is somehow special. These integrals of motion, they, for example, have large localization length. They are broad. That's why they have large error. But this is not what you see, actually. You see that they are pretty typical. They're not very special in terms of any structures that you see. But what's special about them, if you plot this, their centers, their position as a function you plot the error as a function of position of Liams, you see that all these bad apples, they're sitting on few groups here and here. And what it means, it especially means that you have two regions in your device which somehow, for some reason, maybe miscalibration, maybe something else, they work poorly. And because they work poorly, you get this big error. So what this means? This essentially means that we can use our device, our experiment, as a sort of benchmarking of our device. And while this error epsilon is much easier to compute just diagonalization of your system, this gives you actually a good opportunity to characterize large quantum devices. And that's an interesting and unexpected result of our study. Okay, that's here all about one-dimensional systems. I want to talk about just a little bit more about two-dimensional systems, and I have some very nice video to show you. Before that, Zlatko, do we have more questions, or are you good to go?
Maybe you can just mention what the significance of having 104 Leoms is. There's a question around what's the minimum number of qubits to see Leoms.
Well, so this, to be honest, you can see local integrals of motion when starting with 15, 20 qubits. So you can do it for small systems. And essentially, there is no very strong reason to go to 104 qubits in one dimension, because qubits do not get very entangled at the end. But it's a very good test. It's like very good run before you go to 2 dimensions, where you have an intuition for these larger devices when you build towards 2-dimensional systems. So I would say 104 qubits is a good example, and especially you can also see these problems here in your device. So it's a good way to test these large devices before you go in for some very serious computation, which is very challenging to understand. Is that a good answer to the question?
Yeah, I think so. Feel free to elaborate, Vector. And a quick one from Miguel, just how does chaos relate to Leoms? How many how many Leoms can a chaotic system have?
So Leoms is something which essentially prevents system to go chaotic, because if something is conserved, you have a ability to predict, and ability to predict is something which is opposite to chaos. So, and again, if you have some number of integrals of motion which scales with number of qubits, you already don't have full chaos. But to completely block chaotic behavior, you probably need a number of integrals of motion which is comparable, which scales linearly with number of qubits. That makes system, well, clearly distinct from chaotic. You don't have like chaotic pockets and Hilbert space, something like this. That's my understanding.
Vector says, great answers. Thank you.
Okay. So now when we practice a bit in one dimension, we go to 2-dimensional systems. And that's where the real interest goes, because there is a lot of debates about MBL in 2 dimensions. And to disclaim, we try to see it. We don't claim that we have MBL, but we have a strong signature that MBL probably, at least for finite sizes, may be present in the systems. So what we do, we assign similar circuit, which we have for 1 dimension, with one exception, because some qubits now have 3 neighbors. This means that we have, instead of 2 layers, have 3 layers of control Z's. And essentially, that's all the difference. And now we can, again, look at the local observables in the systems. And this is a nice picture showing 2 different regimes. One regime looks more like a localized one. So again, it's 0.1 pi, and we probably expect system to have many-body localization for smaller pi's, for smaller angles. But already for this system size, we believe we can see some proximity effects. So we can see MBL signatures here, and we see them as a conservation of pattern, which we see in local observables, while again in a ergodic system everything goes pretty quickly, or local observables become close to 0, which is nice signature. We can also plot this charge imbalance, which we exercised in the previous slides, and again we can see that we have a slow dynamics here. We don't have a signature that goes to plateau, but we see some low dynamics. So we can attempt to find out local integrals of motion in this scenario. And this is the result. So what happens? We do find such that system does have very well conserved operators. So that's why we see the conservation of pattern. And here you see the examples of this integrals of motion defined, for example, for this neighborhood or this neighborhood of your circuit. They look slightly different. You see that this looks more delocalized than this one. And you can also study the profile of these ones. But essentially, the features you see in one dimension, they survive for 2 dimensions as well. For example, you see that you have exponential diminishing distribution contribution for more non-local Paulis. And similar to 1 dimension, you can also define essentially the precision which you define the limbs using the same measure which we did before. And again, you see that here we a little bit have more limbs sitting on this failed side, means that the effect of noise in 2D is larger, and you can actually confirm that theoretically the effect of noise should be larger, but we still see plenty of limbs that are sitting on improvement side, which give us a pretty clear picture that many of them were derived with a high precision and contain some information about the system. And finally, you can also, in the same way we did for 1 dimension, you can look at this heat map showing the error of limbs sitting on with center as a particular qubit. And again, you see there are 2 hot regions, which probably is the same hot regions we see in 1 dimension because we're using the same device, which most likely contribute to these errors which do fail. And again, nice way to benchmark our device. So let me just summarize. I think we on time. And so during this talk, we learned that local integrals of motion can be used to describe certain quantum systems. And we recreated a system which is quasi-integrable. And we measured local integrals of motion with certifiable accuracy in 1D and 2D. I think there are 3 major goals which we hit with this project. We first proposed, not proposed, I think it's existing literature, but we emphasized and reimagined the way of characterizing systems using integrals of motion. So we come up with this scheme that allows you to do some sort of tomography of quantum dynamics, which is not exponentially hard, but works only for very specific class of systems. We also use a benchmarking. We invented some new ways of benchmarking devices. And finally, we seen something new in MBL physics in 2D, which is, I think, very valuable. And there are a lot of future improvements which we can do. We can do improvements in architecture. For example, we can replace our control Z gates by RZX gates, which have lower error and allow us to go to deeper circuits without compromising in the quality of the device, of the observable. We can also try to target our experiments such they become more challenging for classical simulations. So I think there's very few improvements in coherent times and system sizes. We can get in a regime which is very, very hard to simulate classically, and when we can finally and without question beat classical algorithms. And finally, we think that this is a good direction to study many-body localization in 2 dimensions. At the end, I would like to thank to my collaborators you see on the screen. I especially want to thank Haimang Zhang and Nikhil Harley, who were our interns during making this project. Haimang now is a full member of IBM, while Nikhil now is in graduate school in UC Chicago. And it's a good reminder that we still have open internship applications. So if you didn't do this, please apply, and you have a chance to work in a great team. I would like to also thank entire IBM quantum team, which supports this amazing infrastructure, which makes all this experiment possible, and also keep it open for public, making contribution to science. And I also would like to thank everybody for your attention. If you're interested to learn more about this project, I keep here the link for our archive, so you can read and maybe get more information. And of course, there's my email if you have some more detailed question about this talk.
Thank you for the wonderful talk. First question from Miguel, and great guys, this is a great time to post your questions now. First question from Miguel: do the Liams have some semi-classical interpretation?
Yeah, it feels like they do. I think so. Integrals of motion, they originally come from this idea of Anderson localization. So in Anderson localization is a similar problem where you have disordered potential, but you have a single particle. You have not many particles, not many spins. Single particle traveling in one dimension. And then essentially, if you look at this Hamiltonian of single particle, you will see that eigenstates of this particle are localized. And you can think about this, the orbitals, which are eigenorbitals, these localized states, to be a kind of predecessor of many-body localization. And now answer the question, can you understand many-body localization quasi-classically? It essentially goes to the question, can you understand Anderson localization quasi-classically? And I think there is a way to understand Anderson localization by considering different trajectories which particle goes when it travels on the lattice. And if you sum these trajectories with the phases, correct phases, you'll figure out that the probability of particle returning on initial position is finite, while probabilities that go far away, it's almost zero. So I think I'm not very familiar with that, but I think similar arguments can be made for many-body localization. Though now you have not single particle, you have this large Hilbert space. You might think about some quasi-classical arguments about this problem as well. So answer is yes.
Thank you, Oles. Quick question from Jeffrey. He says he'd like to understand how you devised how many circuits you needed to run.
So in this experiment, actually, we have a pretty impressive number. For entire experiments, including imbalance, O1 particle density metrics, and Liams, we run around 350,000 circuits, large amount. And most of them, because we did some elaborate error mitigation, which brings us around factor of 10 to this number of circuits, because we need to run many circuits to mitigate the noise. But also we have plenty of circuits because we're essentially learning a lot of data points about the system. So the full version of experiments are quite expensive in terms of circuit runs. But it's important that if you ask some simpler questions, for example, you don't ask about all operators, but maybe just single qubit contribution to this local integrals of motion, the experiments becomes much, much cheaper. I think it will be thousands of circuits or so. So depending on the question, you can find number of circuits from 1,000 to tens of thousands, depending on what you want to measure. And plus, you multiply by factor like 10 due to error mitigation.
Right, and from Bektor, is it possible to have a general recipe for Liams, or I guess how does this potentially change as the Liams get broader? Or
it's a very good question. So yes, as Liams get broader, so let me, I don't know if I can jump. I remember there was a slide where I explained how many circuits we need, and I said that we greatly exploit the fact that we have local integrals of motion, and we can input states which are correlated, and we can make measurements which are correlated. And as you increase the size of your Liams, essentially, and this inevitably happens if you go closer to phase transition point, then you get less correlated states in the input, and that brings up the cost of your experiments up until our trick becomes not very useful, and you have to do this random sampling of initial states and random sampling of measurements, which can be quite expensive. But then you can do it. So again, depending on questions you ask and which coefficients you need to find, you can do it with this large number of experiments. And good news is that if you don't want to include more and more power lists, which have exponential amount, and if you limit your attention only to few power lists, the cost, if you look at scaling, it only scales logarithmically with number of qubits at the end. It should be very large. It's like 1.6 million, but this 1.6 million with size of qubits, it remains almost flat. So my summary is, as you increase the localization length, your cost go quickly up until it reaches this barrier where you do random sampling, and then it grows very slowly, unless you want to learn entire Lioms and measure exponentially many Pauli operators. Then that will become exponentially hard.
Right. Thank you, Alice. I think that's all the questions we have time for today. Thank you, Alice, for the really wonderful presentation. As you know, I'm particularly happy and proud of this work, and you've done a marvelous job presenting it and spearheading it. So with that, folks, maybe I'll let you, Alice, leave us with any final comments that you would like to.
Yeah, I would like to just thank everybody for being here, and also I would like to thank Zlatko for being part of this project. And I wish everybody to have a nice day wherever you are. And thank you very much for listening.
All right, folks, there you have it. With this, we will see you next Friday at noon Eastern Time. This video will stay recorded, so you can always go back and rewatch it. The brilliant presentation by Oles Stanko. And with that, we'll see you next week.